Hello and welcome to this video in which I explain measurement models of classical test theory. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including factor analysis, structural equation modeling, multi-level analysis and latent class analysis. And I also sometimes address topics in measurement and psychometrics such as classical test theory and item response theory. If this is something that interests you, then please consider subscribing to this channel. Also, don't forget to check out the description for additional resources, including workshops that I teach for QuantFish. Now, in this video, I want to address the question of what are the different measurement models of classical test theory and how do they differ? And so this is a little bit different from how classical test theory is often viewed or is often taught. Like oftentimes in a standard psychometrics course or measurement course, you will just learn, okay, classical test theory has Cronbach's alpha and you can calculate that in SPSS, and there you go, that's your reliability. And then there's maybe also something like a split half reliability coefficient and or a test-retest reliability coefficient, and then that's pretty much it. So that's how we determine reliability. I like to look at classical test theory differently in terms of an actual measurement theory and in terms of a theory that provides us with formal definitions of the concepts that we need to know about, such as a true score variable and an error variable, as well as that provides us with measurement models that we can actually test for our observed data and that give us the parameter estimates based on which we can then, if the model fits, determine, for example, reliability. And so therefore, in this video, I want to address measurement models of classical test theory. Now, first of all, let's talk a little bit more about what is classical test theory. And I have a separate video in which I go much more into the details of the concept of classical test theory here on this channel, so feel free to also take a look at that. I have a whole playlist on measurement and psychometrics that you can check out, where I have a lot of videos on classical test theory and also item response theory. So here, just real quick, I want to review what classical test theory is and what it does. It is a theory of measurement, specifically a theory of measurement errors and unreliability of scores. In the theory, we are provided with mathematical formal definitions of what a true score variable is versus an error variable is, how these variables are defined. And also based on those definitions, we can then come up with a definition of reliability. So how can we capture reliability mathematically in a single number with an equation? That's part of classical test theory, that we want to find out to which extent are our scores contaminated by random errors of measurement. And so that then we want to quantify using mathematics, using mathematical models and equations, and the reliability coefficient is one key measure in classical test theory that allows us to determine the reliability, the precision of our scores in questionnaires and in psychometric tests. And then finally, and that's the topic of this video here, classical test theory not only provides us with formal definitions of true score and error variable and reliability, but also allows us to define statistical measurement models that we can test against our observed data. And this is a little known fact. So typically, or oftentimes, it's one criticism of classical test theory that people will say, oh, that's not testable, it makes untestable assumptions, and that's really not true. So there are many assumptions in classical test theory that imply testable consequences for the observed data, and those are inherent in or implied by the measurement models that I will discuss here in this video, where we can very clearly say, okay, what do the data have to look like in order to meet the assumptions of a given measurement model. And so we can test the models, for example, with confirmatory factor analysis, with a chi-square test of model fit to see if those models are adequate for our test scores. And then based on those models, if they fit well, we can, for example, determine the true score variance, the error variance, and the reliability coefficient. And I have more videos on those topics as well, how this is done in Mplus, for example, and other programs for structural equation modeling, where we can fit classical test theory models as confirmatory factor analysis models. So let's dive into it and let's take a look at measurement models of classical test theory. Before we do that, it is important to realize what the basic classical test theory decomposition of observed scores is. So in classical test theory, we consider test score variables yi here, so say for one test, so y1 represents the observed or measured test score variable for a given psychometric test. For example, a measure of academic intelligence, so this could be an IQ test. And the idea is in classical test theory that we have, in order to fit measurement models, more than one test. So here we have a second test, Y2, so this could be a parallel IQ test that also measures academic intelligence and for which we also collected the scores. Or Y1 and Y2 could be subscales of the same IQ test or test halves. Or even under certain circumstances, Y1 and Y2 could refer to different items of a given test, as long as we can assume that those items are on a continuous scale level, meaning that these variables Y1 and Y2 are metrical or interval scale. And so then, in classical test theory, in the basic decomposition, each test score variable has its own associated true score variable, tau. So here that's tau1 and tau2 for the two test score variables Y1 and Y2. And these true score variables capture the person-specific effect, meaning the trait that is causing variation in the scores. So differences between individuals in their, for example, intelligence trait cause some of the variation in the test scores. But in addition, there's also random measurement error, random noise that also causes variation in the test scores between people. Because, so say, some persons might actually have the same true score, the same true intelligence of, let's say, 100, but for one person, measurement error causes the observed score to be 103, and for the other person, the score is caused to be 98 by measurement error. So there's a discrepancy in the observed scores, meaning there's some variability between people in the scores that is not due to true differences between individuals, but rather that is caused by measurement error or random noise. And so that's captured by the epsilon measurement error variables on the left-hand side here of this path diagram. Now, this basic classical test theory decomposition has the limitation that it doesn't lead to an identified statistical model, because we would have too many unknowns. With two observed variables, Y1 and Y2, we only have two variances, one covariance, and two means as pieces of available information from which we could estimate parameters. But in this model here, we already have two true score variances to estimate, two true score means, as well as two error variances, and then potentially also the covariance between tau1 and tau2 we would want to estimate. And so we don't have enough information with just two variables to estimate all those unknowns, all those parameters related to tau and epsilon. And so therefore, we need to make simplifying assumptions, and that leads us to the measurement models in classical test theory. So that's where they come from, is for, so say, the need for identification, the need to reduce the number of unknowns so that we can actually estimate parameters such as the true score variance and the error variance and other parameters of the models that are related or that are relevant for classical test theory psychometric analyses. So let's start with the most restricted model in classical test theory, the most simple, the simplest measurement model of classical test theory that makes the most restrictive assumptions. So what assumptions does this model make in order to simplify or reduce the number of unknowns in our basic decomposition? The first assumption is the assumption of Tau-equivalence. Tau-equivalence means that we're assuming that different tests, I and j, measure the exact same true score variable tau. So tau I is equal to tau j for all ij, means all tests that we consider measure the same latent ability, so to say, the same trait. In our case, we would assume that the two IQ tests, 1 and 2, measure the same underlying trait of intelligence. And so then we can simplify the model, or that simplifies the model, because now we will only have to estimate one true score variance and one true score mean, not a separate true score variance and a separate true score mean for each tau, and also not a covariance between tau 1 and tau 2 if we reduce the number of true score variables down to 1. So that's already helpful. And then assumption 2 is the assumption of equal error variances in the strictly tau parallel model, which means that all epsilon variables have equal variances, meaning the same amount of measurement error variance is attached to the different yi and yj variables. And then finally, the third assumption is that the error variables are uncorrelated for different tests. So the covariance between epsilon 1 and epsilon 2 in our simple model would be assumed to be 0. And that is the case for all ij. So for different tests, the error terms cannot covary, cannot be correlated. And so then this model leads to a simpler structure in the path diagram, because now we can replace tau 1 and tau 2 by a single common factor tau, a single common true score variable, and then we have only one tau in our path diagram. Both the factor loadings here are implicitly fixed to 1, because the measurement error equations, the measurement equations that you can see here down below do not contain a factor loading, so it's implicitly fixed to 1. So in a strictly tau parallel model, we have a single factor model with equal factor loadings and equal error variances, which you can see here in the diagram. So because the variances are not directly included here, but so the assumption is that epsilon 1 and epsilon 2 have the same variance. And so then this model has only 3 parameters. It only has the true score variance parameter, the true score mean parameter, and one error variance parameter. So 3 unknowns, 3 unknown parameters that have to be estimated, but it does have, with 2 variables, 5 pieces of information, 2 means, 2 variances, and the covariance between y1 and y2. So in the observed data, we have 5 pieces of information. This model estimates only 3 pieces of information. So even with just 2 variables, the model is over-identified with 2 degrees of freedom and leads to a testable constraint or testable restriction. And we will discuss shortly what that means. So this is a confirmatory factor analysis model that is over-identified and that you can test against your data, contrary to what many people think in terms of classical test theory not being testable. So this model is testable already with 2 variables, and of course also with more than 2 variables. You would even have more degrees of freedom. Now, what are the testable model implications of the model? Given that we assume that the variables share the exact same true scores, that they have the same error variances, and that they have uncorrelated error variables, we have the implications that the y variables, the test score variables, have to have equal means, they have to have equal variances, and they have to have equal covariances in the underlying population. So those are all testable restrictions. So with 2 variables, we're assuming equal means. That's where 1 degree of freedom comes from. Also with 2 variables, we're assuming that the 2 variances are equal, which leads to another degree of freedom. Now with 2 variables, we don't have multiple covariances, or there's only 1 covariance, and therefore the last constraint here or testable implication does not apply to the design with 2 variables. But if you had 3 variables, y1, y2, and y3, then you would have 3 covariances, and they would all have to be equal for the model to be adequate for your data. So that would constitute another testable restriction with 3 or more variables. And then also, since the variances in the model are implied to be equal, also the correlations then have to be equal if the covariances are equal and the variances are equal. And that leads to a very nice simplifying feature of the strictly parallel model, and that is that the model also implies equal reliabilities. And moreover, the reliabilities are equal to any correlation between 2 strictly tau parallel variables. So you could take any correlation, and that would give you an estimate of the reliability of each of the variables. The correlations have to be equal within sampling error, equal in the population, and therefore the variables also have equal reliability. So it's a very nice simplistic model. However, it's also a very restrictive model, and it's easily rejected. For example, if your variables have unequal means, so meaning if the IQ tests differed in their difficulty, then they might have different means, and then a strictly parallel model already might be rejected by a test of model fit. Or they may not have equal error variances because the scales maybe differ in their reliabilities. And then also that could lead to failure of this model. And therefore, classical test theory offers additional models that make less restrictive assumptions than the strictly parallel model. The next model then in the logical order is the essentially tau parallel model. So you can see that that already softens up the tau parallel assumption. It's no longer strictly tau parallel. Now it's essentially tau parallel. Now let's take a look at what that means for variables to be essentially rather than strictly tau parallel. And so essential Tau-equivalence means that we are allowing for a constant difference between the true score variables for any given pair of tests. So tau I is equal to tau j plus a constant alpha ij. So this means now the tests can differ in difficulty, in their means more specifically stated. So the alpha ij constant allows us to take mean differences into account if our IQ tests, for example, differ in difficulty. If one IQ test is harder than the other, then this would mean that people on average score lower on the harder test than they do on the easier test, and then that would jeopardize the assumption of strict tau equivalence. But essential tau equivalence may still hold, where we're allowing for a mean difference between the yi and yj variables. The second assumption is the same as before, equal error variances, so that is unchanged. And then also the third assumption of uncorrelated error variables is also unchanged relative to the strictly tau parallel model. Now the essentially tau parallel model then in terms of a path diagram looks the same. So still the loadings are fixed to 1 and therefore are not shown in this path diagram, and the additive constant or intercept here, alpha I, that would differentiate each individual true score variable from the common true score variable here, is also not shown in this path diagram because alpha I refers to the mean structure, and so in this path diagram I did not include a representation of the mean structure. However, the measurement equations for the observed test score variables look different. They now contain an alpha constant, additive constant or intercept parameter, as you can see here. Here's alpha 1 and here's alpha 2. And so in the simplest possible specification of such a model, these constants would just simply reflect the means of the observed test score variables. If we set the latent mean to 0, which many structural equation modeling programs do by default, then, so to say, the tau mean is fixed to 0 and the intercepts are estimated, and then they simply equal the observed variable means. So because of these intercepts, the testable model implications of the essentially parallel model are a little bit different. Specifically, we're no longer assuming equal yi means, but we're still assuming or implying equal yi variances, because the error variances are still set equal for all tests. And we're also still assuming equal yi covariances and equal correlations because the variances are also equal. And so that means that we still in this model have the feature of equal reliabilities and also of simple computation of reliability by means of this parallel test correlation. Correlation yi, yj can be used in order to get an estimate of the reliability of each test. So it's still pretty nice. It's a little bit less restrictive than the strictly parallel model because now the tests can differ in their difficulty, in their means. Previously, that was not allowed, but we still maintain that the tests have equal reliabilities, which is a nice simplifying feature. Now, Still, this model can be tested against the observed data. We still have 1 degree of freedom left because of the assumption of equal variances. So even with 2 variables, that's testable. And so this model then would still be over-identified even with only 2 test score variables, and we could test this assumption of equal variances. Now, neither the strictly nor the essentially parallel model may fit our data, right? So there may be also differences in terms of the variances and or the error variances between tests. Specifically, or otherwise stated, we could say that different tests may have different reliabilities. If you're using different IQ tests, they may not have the exact same measurement error variance component. And so subsequent models relax this assumption of equal reliabilities by no longer requiring error variances to be equal. And so the next model that I want to discuss here is the Tau-equivalence model. The Tau-equivalence model makes the same assumption of Tau-equivalence with regard to the true score variables as did the strictly parallel model. So now we're going back there a step. We're taking the alpha constants out again for the Tau-equivalence model. We're now still assuming equal means. However, we're no longer assuming equal error variances in the Tau-equivalence model, and instead we only maintain the assumption of uncorrelated error variables, which we actually maintain in any classical test theory model. So this assumption here, the last assumption, is always made in all of the models. Now, the Tau-equivalence model then leads to a path diagram that again looks the same. Again, we have loadings fixed to 1 in this model when it's estimated as a confirmatory factor analysis model. And we're still assuming that there's only a single common true score variable that is identical to all of the individual true score variables. And our measurement equations look the same as in the parallel model, or strictly parallel model, I should say. However, the error variance parameters, which are not explicitly shown here, they are now allowed to differ between variables. So the variance of epsilon 1 can now be different from the variance of epsilon 2. And so this then also leads to a reduction in the number of testable implications of this model. So with this model, we only have the implication of equal yi means because we're making the assumption of tau equivalence where we don't have a constant alpha ij, and so therefore the variables are not allowed to differ in their means. However, they would be allowed to differ in their variances. So that's allowed, but not in their covariances. So with tau equivalence, we have the assumption of equal means and equal covariances. Again, the assumption of equal covariances can only be tested when you have 3 or more test score variables. Otherwise, with 2 variables, you have only 1 covariance. So there's no testable implication there. However, with 2 variables, you already have 2 means. So we can test the assumption of equal means. And that leads to 1 degree of freedom still, even when you consider only 2 test score variables, y1 and y2, you still have 1 degree of freedom. So even the tau equivalence model is testable in this small design with only 2 tests. Now, another thing that's different now is that the tau equivalence model no longer allows us to calculate the reliability as the correlation between the 2 tests. So that is only possible under the strictly and essentially parallel models, not under the tau equivalent model. And the reason for that is that the tests now can have different variances and different error variances, and so they also can have different reliabilities. The reliability is now estimated as the variance of tau, which is a model parameter that gets estimated, divided by the variance of tau plus the variance of epsilon for that given test. So the parameters are used from the model, the true score variance component and the error variance component. Those can be found in the output when you estimate this model, for example, in Mplus or in Lavan, and then you can calculate reliability based on the variance components, or also most programs will give you R squared based on the standardized solution. And so when you look at R squared, then that also is equal to reliability for the tau equivalence model. Next is the essential Tau-equivalence model. The essential Tau-equivalence model now adds in another parameter that we previously already learned about when we looked at the essentially parallel model. And so say the first assumption with essential Tau-equivalence is again that the variables, the true score variables, can differ by a constant value alpha ij. So that parallels what we did in the essentially parallel model previously. So now we're again allowing for mean differences in addition to variance differences between the different tests. And then the second and last assumption again is the assumption that we always make, that the error terms are uncorrelated for different tests. The essential Tau-equivalence model then has this alpha parameter again, so an intercept is added to our model. The path diagram looks the same because the loadings are still fixed to 1 even in this model. And the measurement equations look the same as in the in the essentially parallel model, where we now have this additional alpha 1 and alpha 2 constant to reflect mean differences between the scales. And in this model, we also are not making the assumption of equal error variances, so the error variances are freely estimated. As a result, this model is saturated when you have only 2 tests, because with 2 tests, again, we have 5 knowns, 2 means, 2 variances, 1 covariance, and now in this model, we have also 5 unknowns. We're estimating the true score variance, we're estimating 2 intercepts, we're estimating 2 error variances. So we have 5 unknown model parameters that are estimated with essential Tau-equivalence. And so when you have only 2 tests, then 5 minus 5 is 0. So the model is saturated, has 0 degrees of freedom, meaning it has no testable assumptions when you only consider 2 tests. However, if you considered 3 or more tests, then even this model would have testable implications, because with 3 or more tests, you have 3 or more covariances. And this model still implies that all covariances between yi test score variables are equal in the underlying population. So it's still testable, but not with 2 variables, because you only have 1 covariance with 2 variables, so there's nothing testable there. But with 3 or more variables, you have testable implications for the covariance structure, even with essential Tau-equivalence. And now the last model that classical test theory offers is called the congeneric or Tau-congeneric model, which is very common in factor analysis. Specifically in confirmatory factor analysis, we often speak of a congeneric measurement structure. A congeneric measurement structure is very general in that it allows not only intercepts but also factor loadings to differ between variables. So that's the standard confirmatory factor analysis measurement model that we use in CFA and also in structural equation modeling. So then let's take a look at the formal assumptions here. The first assumption is the assumption of Tau-congenericity. So that's different from previous models that all made the assumption of either Tau-equivalence or essential Tau-equivalence. And now we're no longer making these assumptions. We're making a weaker assumption about the homogeneity of the true score variables for different tests. And so namely, we're only assuming that they are linear functions of one another, so that tau I is equal to a multiplicative constant lambda ij times tau j plus an additive constant alpha ij. So the true score variables are positive linear functions of one another. So it is still required under this assumption that the true score variables for different tests be perfectly positively correlated. So it's still an assumption that they measure a common factor, but they can differ not only in their means, but also in their units of measurement. So that would be relevant if you measured, for example, intelligence with different tests that came in very different metrics, where one test maybe has a score range from 50 to 200 points, and another IQ measure has a score range from 0 to 80 or something like that. Then they would have different units of measurement and also potentially or very likely would have different means. So in that scenario, when you have different variances covariances, different means of those different tests, then you have to also have a multiplicative constant that accounts for scaling differences between those tests. And so that's then the standard model that is used for measures that are supposed to be measuring the same underlying trait, however with different units of measurement. And another example could be when you have two scales where one measures weight in ounces and the other scale measures weight in kilograms, then also you would have to have a model like this, or of temperature in Fahrenheit versus temperature in Celsius. Then this model allows you to do the conversion between the underlying true score variables that are in different units of measurement. The second assumption is the same as always, which is the assumption of uncorrelated measurement error variables. The Tau-congeneric model with this multiplicative or loading parameter still assumes that there's an underlying common factor tau without an index, and so then each variable has a factor loading lambda I and an intercept alpha I, so the variables can differ by a multiplicative constant and by an additive constant from that common true score factor. And so then in the model we typically depict the factor loadings lambda 1 and lambda 2, which here in this model would be freely estimated, at least some of them. Now, the measurement equations then look like standard measurement equations in factor analysis, where we have observed variables on the left-hand side, and on the right-hand side we have an intercept plus a factor loading lambda times a factor here called tau plus an error term or residual epsilon. And so this model is more demanding in terms of model identification because it has the lambda parameters as well. And so one thing that we have to do is we have to either constrain one of the factor loadings to 1 in a given measurement model, so use one variable as reference for which the lambda is fixed to 1, or we have to fix the factor variance to 1, the true score variance to 1, in order to identify all the loadings. So that's one thing that is special about this model, is that we have to still think about how to identify the loadings. And then also this model is not identified with just two variables. There are just too many unknowns when you have only two variables, unless this model is part of a larger model where the tau factor is correlated with another tau factor or with another observed variable such as age or gender. Then this model could be identified even with different loadings. However, when you estimate this model in isolation with just two variables, it would be under-identified. It is just identified or saturated when you have when you have three variables. So with three tests, this model is saturated or just identified unless you have another variable in the model, in which case it could be over-identified. With 4 or more variables, the Tau-congeneric model would be over-identified, and it does have a testable restriction also with 4 or more variables, namely that certain ratios of covariances are equal. And you can see that depicted here. This is the testable restriction of this model, that these complex ratios of covariances have to be equal under the model. So that's less intuitive than previous assumptions where they were simpler and they simply meant, okay, covariances for different tests are equal. That's no longer required, but those ratios are required to be equal, and that's a testable assumption with 4 or more variables when you fit the congeneric measurement model. In summary, we have 5 models of classical test theory here ordered from the most restrictive model to the least restrictive model, with some of the models here being the same in terms of the number of parameters versus restrictions, but the strictly tau parallel model is definitely the most restrictive model. The Tau-congeneric model is the least restrictive model. You can see that the models make increasingly less restricted assumptions, beginning with strict tau equivalence, equal error variances, and uncorrelated error variables, and then loosening this assumption of tau equivalence to essential tau equivalence, then loosening the assumption of equal error variances, getting rid of that, and then finally also getting rid of the assumption of strict tau equivalence or essential tau equivalence and making that into congenericity, where the variables, the true score variables, are merely positive linear functions of one another. And so you can see that that has consequences for the implications or for the restrictions that are being tested with the models. It starts with a very restrictive set of assumptions where the variables have to have equal means, equal variances, and equal covariances in order to be strictly parallel. They only have to have equal variances and covariances in order to be essentially parallel. Subsequently, for tau equivalence, they only have to have equal means and equal covariances. For essentially tau equivalent tests, they only have to have equal covariances. And for congenericity, they only have to meet this requirement of equal ratios of covariances that is shown again here. In terms of reliability estimation, the 5 models use almost all the same equation for estimating reliability as the ratio of common true score variance, variance tau, divided by total variance, variance y. However, notice that in the congeneric model, the equation is a little bit different because you have the factor loading, lambda I squared here as well in the numerator. So that's a scaling parameter that is needed in the congeneric model because the variables can be measured in different units of measurement. They can have different variances. And so as a result, too, we have to scale the true score variance in the reliability formula by lambda squared. Another special thing with the reliability is that with the strictly and essentially parallel models, as mentioned previously, you can replace the reliability estimation formulas shown here with the correlation between any 2 tests. So under the model, all variables should have the same correlation in the population, and each of those pairwise bivariate correlations between test score variables gives you an estimate of the reliability. Now, another feature of all classical test theory models is that they allow you to also determine composite reliability, meaning the reliability of the aggregate of all of the parallel or tau equivalent or congeneric tests. And different composite reliability formulas apply to different tests. I have a whole set of videos on this channel as well on composite reliability if you're more interested in that in detail. I show some issues and I explain composite reliability in more detail, so feel free to check that out as well. Here I only want to mention that with essentially and strictly tau parallel tests, you can use the Spearman-Brown formula to calculate composite reliability easily. So the reliability of the sum of the 2 tests, for example, or the sum of the however many parallel tests that you are looking at. When you have essentially or strictly tau equivalent tests, then you would use Cronbach's alpha. In that case, Spearman-Brown no longer applies because the variables can have different variances and different reliabilities, and so you would use Cronbach's alpha for essentially or strictly tau equivalent tests. And finally, for congeneric tests, a common measure of composite reliability is McDonald's omega that takes into account the different loadings of the variables under the congeneric model. I hope you found this video useful to learn about measurement models of classical test theory. If you want to learn more about classical test theory, feel free to check out my playlists on this channel on classical test theory and measurement and psychometrics. Also, check out the description where I have some courses listed that we offer through QuantFish on psychometrics, including classical test theory and item response theory. Consider subscribing to this channel if you like these topics, and I'll see you next time.